Hey guys, so in this video, what I'm going to do is show you how to develop end-to-end system design. What we're going to be focusing on is a holiday search and booking platform. So you can see here on the screen, I've created one with Miro and we're going to go through everything in detail. So don't be worried about anything to do with what you see here. You might not know everything on here, but what we want to do is break it down into small, simple steps. And then I'll explain each concept when it happens and how I kind of built this from scratch. So again, utilizing AI as well for any relevant questions that you have or any trade-offs or anything like that. As a engineering lead, I think about all of these end-to-end scenarios. Now, if you look here, I've kind of put scalable, highly available, secure, event-driven, eventually consistent search slash strongly consistent booking as well. But what I want to do is this is the end goal from starting to this kind of end to end final architecture, and all of the individual sections here have trade-offs as well. So now you can see this is the end goal. What we want to do is we want to break this down into smaller chunks, and I'm going to show you how I got from the start to this end process, and then I'm going to do some YouTube videos around explaining all of the concepts so that you understand what it is at a higher level. But again, there's a lot of end-to-end security, consistency, availability, all of the abilities basically on considering things for end-to-end solution design itself. Holiday search platform itself or a booking platform is not just a front end that you have with a React app and then a back end with Node.js that connects to a database, for example. There's a lot more to it, and something like this is what a principal engineer would look at. And I want to show you what goal looks like in terms of getting that thinking element in place for being an engineering lead or a principal engineer or a staff software engineer. These are the kind of things that we want to cover. What I'm going to do is go into it further so I can scroll down. I've got like the principles in place and the kind of functional requirements. But if we scroll up as well, you can see this is how it works, and then the user or the request works, how the search indexing happens, because there's different types of indexing that goes on within databases, cap theorem, what we want to do and the simple view for it, the API design, and then finally how the search works. So we'll get into all of this next. So I've gone through the actual initial kind of draft of what I've done here. Now I want to kind of break this down into like the sections. So I've got the functional requirements and then the non-functional requirements over here. So let me just add some more dashes on so you can see a bit clearer what's going on. All I've done is kind of neatened it up a little bit. So search, users can search for holidays by destination and so on. It uses full text search via Elasticsearch. So Elasticsearch has its own cluster. It does inverted indexing and it basically finds the relevant destinations that you've typed in, or the hotels, or whatever it may be, through autocomplete suggestions or the title and text searches that it offers. I'll go through Elasticsearch in detail in another video. The departure airports are filtered using exact keyword matching. So again, this forms part of your query. So like Manchester, this one is Lahore, and then this one is, I'm not sure, but you get the picture. And then flexible date search is supported through date range filters. So only give me back the holidays between a range of dates and times. These are the ones. And then you can do further filtering and sorting like your afternoon flights or your morning flights or whatever it may be. Elasticsearch takes care of all of that. I would put in here Elasticsearch in all of it. But most of the time you could, like I mentioned in the previous video, you could do multiple queries to other places. So you could add something like a write into your Postgres database, and then that then syncs with your Elasticsearch database or your to update your documents within your Elasticsearch cluster. There's a lot going on right now, so that's another thing. And then autocomplete suggestions are returned for destination names and hotels, which again we did the GraphQL query. It kind of refined with the auto text search with Elasticsearch. Holiday and availability. So users can view holiday details, including itineraries, images, facilities, and reviews. This is part of the requirements. And real time availability and pricing is validated before booking is confirmed. So again, we'll think about having a booking API, an availability API, an autocomplete API. If we wanted to break it down granularly, these are all services that we have, and an inventory hold is created before payment is taken. So what does that mean? Well, if I wanted to book a holiday, I need to think about things like room availability. So let's say I've gone through the whole process of booking a holiday. So let me just actually do that with on the beach, for example. Let's go into here and you'll see this play out visually. So we're searching for a holiday. I've done the search. So the search is again highly available and not consistent because the results would be cached. These are all the information I've got in here. So I want to select and see more details, but I want to look in the URL. You can notice a change that will happen. So see more details, and you can see that instead of results now, it kind of said, and then this is the specific holiday ID over here, and then the query happens over here. So now when I book the holiday, what I want to see is some sort of information saying these are my extras, and I've got all of the information payable on the beach per person is this. But what I want to do is do my add-ons. All of this information will add in to the overall package. So you can see there that price change over here. But then when I continue to check out, there will be some sort of like a rooms API or whatever it may be that we connect to with third parties. For example, the hotel gives us information such as there's only 3 rooms available for this holiday between these dates. And then we say, right, okay, when we do continue to check out, we'll have some sort of timer on there to say, right, you've got 20 minutes or whatever it is. We're going to put that booking on hold. That room will go from 3 to 2 for everyone else, but for you, we're going to reserve this room, right? In that 20 minutes, if you don't select that room, for example, then that kind of timer would disappear and then that room will go, or the availability will go from 2 back to 3 again. So if I could click continue to check out, now I should kind of have some sort of timing in there, probably towards the end when it's the book stage here. Actually, it's here. So I've got an hour to hold that information in. So that means I need some sort of kind of ticketing system or whatever it is to kind of say, almost like a ticket lock service where it says, right, there's a status on this booking now, it's on hold. So if you go into the final design, I'll show you what that I mean by that. So if I go into here and scroll down and find my booking service, you can see here. So booking state machine, I've got pending inventory held. Yes, that's right. Then I've got all the kind of payment authorized states, which are supplier failed, payment release failed, and then supplier confirmed and then confirmed. Once it hits the confirmed section, that means that the hotels now are from 3 to 2. So therefore, we then update the relevant API that we have. So this scenario might be PostgreSDB that updates, and then the Elasticsearch DB updates later based on the event bus that we create, which I'll talk about later on. But that's essentially what it is. I don't want to go into it more detail than that for now. Booking, again, users can create and manage bookings. Again, I mentioned the inventory part. And then when it comes to booking, users, we've talked about this. I mentioned booking follows a state of pending, inventory held, payment authorized, supplier confirmed, and then finally confirmed. Then what happens is payments are processed via Stripe, but it can be any provider using their iframes that you make the API calls to. And then idempotency keys prevent duplicate bookings. So this means if I'm that customer that I'm making this booking on, let's say for example, I'm making this booking here now, I don't get charged twice. It'll just happen once as a transaction and that's final. So that's why we need the idempotency key. So let me just go back into here, and then users can register, log in, manage basic CRUD methods here, but you need some sort of authentication with JWT authentication here, which means then as a user, I can then go into it, manage my holiday booking, and then that again transactional thing where I don't need Elasticsearch DB for that because the search is already done. I need some sort of management service where again, I'm going to refer to Postgres because that's probably the most scalable one. And again, you can use something like Cloud Spanner, GCP, which is global, highly available. It can scale, it's got replica sets that you can have, and so on. So, if you think about it and break it down into detail, like a high end architectural exam or a design, these are the kind of questions you will get asked on thinking about the solution end to end. And this is where the principal level engineers would come into play. So, you need to think about all of this kind of information. So, break it down to this T, but then you need to understand the trade-offs involved. If I use this service, what's the impact involved, and so on. So thinking about that is very, very important. So that's the functional requirements. I'm just going to pause it there and let's think about that. These are the questions that you would ask your product owner or business person that you're working with to say, does this make sense? We need to ask these questions. Does this make sense to you? Are there any other changes that you need? These are the questions you need to ask. And then based on that, we can then do our non-functional requirements. So like, for example, in this design over here, I know I need to do more reads to a date than writes. So yeah, again, I need to know that, do I need more reads than writes, or do I need to do more writes than reads? And then that determines what databases you would use, and then the kind of indexing involved in whatever it is you need. So like your inverted index for your Elasticsearch or your B tree indexing for your SQL database, whatever it is you need to think about, all of the information, all the considerations involved. So that's the functional requirements. What we're going to do next is look at the non-functional requirements. So let's go ahead and get started with that. So this is essentially how you earn your kind of keep when it comes to becoming like a principal engineer or understanding how everything works from, high level. I've got these functional requirements. Now I need to kind of distinct myself and understand the processes and the kind of structure in order for me to get a robust, scalable environment for everything to do with the functional requirements in order to thrive. So again, I've got all the non-functional requirements in here, such as performance, availability, scalability, all of the utilities, and we'll discuss them. Search P95 latencies, or what are the standards for me to kind of get the search latency, and I want that to be less than 300 milliseconds. Utilizing Elasticsearch for this, utilizing in-memory store such as Redis to get cached information for a query has kind of been utilized quite often. So that's important. Index lag should be less than 30 seconds. Again, the inverted indexing in Elasticsearch, we need to kind of have some sort of monitoring in place to say, right, these are the standards for performance. I want it to be less than 30 seconds. So before, if we looked at the On the Beach page, it kind of said loading your holiday or searching for your holiday. So if I did it here and I selected, for example, King's Cross, and then I changed the dates in here to this, and then I changed this to for adults over here. Let me just clear this, and what I want to do is just press search. It took me quite a bit there to kind of get that kind of search query, and now you can see what's happening here. So it's kind of loading in increments the information, so some paginations going on, but what it does is the first three you saw there, they were the recommended. So what actually happened here? So let me just find this. Does it have anything to do with recommended? It does, because it's not clearing. If I go into here, and there will be some sort of recommended, but this should be cached because the recommended ones for this particular location, they will be served closer to anything. So that would mean that there must be a cache because these appeared first and then these ones loaded and lazy loaded after. There's definitely some sort of pagination going on, and when I scroll, the CDN is loading all of the static images from the location. So as a non-functional requirement for performance, I want the search index lag to be less than 30 seconds, and then the booking confirmation, I want that to be less than 5 seconds. So that means thinking about something like Kafka or Eventbrite have a transactional output where if I made the booking, that's all I need to do. Anything else is with a pub sub framework where GCP has a pub sub kind of service, which is similar to Kafka, where it kind of does the transactional messaging and the messages to the subscribers of the topic that it creates. So in here, we would have a booking topic that everyone subscribes to. For example, your notifications, your emails, your booking confirmation, the room numbers going from 3 down to 1. All of this is done asynchronously, not dependent on the booking time. The booking will then kick off all of these kind of async operations. So that's why we just want to care about the booking first and foremost. The payment, has it gone through? That's fine. The customer's booked in now. So that kicks off the kind of topics that we'll cover later on with Kafka, I think it was, that I used in this design. The availability. So this means how available are the services within my application. So I want search to be available 99.99% of the time. on the odd occasion, if something goes down or I need to do an update or whatever it may be, I then kind of separate or create a shard within the database, or whatever it is, a section in the database that says, right, this is going to be serving a low traffic time, such as between midnight and 5 a.m. That time will say half the database is going to be updated, or a third, or whatever it is, and then you do your batch updates within that time frame of whatever it is you need. For example, if I'm adding a column to a Postgres database that has like 10 million users, then how do I add that column? So you would kind of add a column as nullable within the database itself, and then you would do your code changes within your actual app itself on your client to say, right, when we do your writes now or your post requests, then it includes that extra column. Let's say I added a column for like ratings, for example. So all the new ones get added, and then you kind of batch add the or backfill the kind of ratings for the other one, which is stage three. And that's done in like little sections so it doesn't interrupt like services that are quite big. So you need to think about all of these things that come into play. So search availability and then booking availability, user needs to be able to book at all times 24/7. So that is it, and they need to lock in the price, which again goes in with the performance over here. Stateless services scale horizontally via Kubernetes horizontal pod auto scaling, but you can deploy your Docker images or your Docker builds with stateless APIs, containers, and that is an example would be something like Cloud Run, where it's kind of auto scaling, but that's just one singular service. For major architectural container orchestration platforms, probably do need Kubernetes, because that manages and scales your apps for you. It has your kind of your monitoring and everything to do with how it kind of replaces pods and your updates and versioning and updating your control plane with your Node.js. All of that kind of information is done via Kubernetes. So it's very important that you scale your applications with something like a container orchestration platform such as Kubernetes, which is why all the cloud services provide that offering. So that is that. Scalability wise, Elasticsearch is sharded and replicated. Sharding is basically splitting your database into like four sections, whatever it is, and then each section sort of shard will be like you would have your shard index for each kind of search query. So you might have a shard index that create has certain regions in it that you kind of then to, and again it's just splitting it out, and then replicating it is just creating the backups for the relevant shards in case there's downtime on a singular shard, or within your Elasticsearch kind of cluster itself. So that's essentially it, and it probably is the same for Postgres, although Postgres uses read replicas for reporting and analytics. So that's just making sure your database is highly available and scalable as well. And then your Redis cluster handles high throughput caching. So when I mentioned Kafka as well, Redis cluster would kind of subscribe to the topic of whatever it is that it is connected to. So Redis cache could be on your booking service, it could be on your search service, it could be on your event service, whatever it is, so that you're not you can serve that quick low latency information to the user. So that's that. And then I'll quickly go through the others. Consistency. So search results are eventually consistent with a short TTL cache, which means every so often update the cache. Every 30 seconds or a minute or whatever it is, the search can be updated for that. And then the booking data again is strongly consistent, which means use your PostgreSQL as your primary data reference point, and then you can use your replicas as the secondary ones. And then finally is your price and availability are revalidated before booking is confirmed. So when we get to the extras page over here, if I'm still on the extras page, so now you can see the countdown is coming down now to 40 minutes. I want to revalidate this final price over here when I'm the final call on here, just to make sure that A, I'm serving the customer with the right booking information, but B, I want to make sure that this number is kind of revalidated once more. And then if I go back into here, security, so TLS everywhere, MTLS within the service mesh, which is Istio, which then it kind of does all of your information to do with your Kubernetes. So if I go into my holiday search at the top here, you can see Istio is the service mesh. it manages your traffic, it does your observability, your retries, and any sort of circuit activities with Nginx. So you can see here the load balance or the API gateway manages the Istio ingress. How does the get managed to the right place? The API gateway almost. So it'll say, I'm going to onthebeach.co.uk slash, I don't know, Turkey. So that slash Turkey will have a service managed by the Istio ingress itself, which is held in the Helm file or the YAML file. And then it will load that service up for the relevant customer that's entering it, and then all of this information within the Kubernetes cluster, it will serve the relevant information for the namespace within the cluster itself. So again, if you don't understand these topics, I'll go through Kubernetes and what that is in another video. But for now, thinking about these things on in especially like traffic management with your Istio ingress is important. Then we've got your kind of OAuth 2 authentication and the RBAC authorization. This is available to the public. So do we need least privilege in here? Probably not, unless it's a logged in user, where then we need to kind of refine the holiday customer has had, meaning the transactional information, the holiday information, the bookings, any extras you've got, the rooms, all of that kind of stuff. It needs to be kind of secure for that particular customer. So that customer will register, have the email that they can log into. All of that needs to be contained within the security of the authentication. So thinking about like your IAM policy, utilizing like your principle of least privilege to the relevant services and so on. And then again, you need some sort of compliance for payments, encryption, thinking about like WAF, Akamai web application firewall, only allow people into the cluster that are only allowed. And then again, stopping like DDoS attacks or cross-site scripting, this kind of information we need to think about in detail. And then secret manager for credentials. So like if I'm getting a key from a file in Key Vault, for example, in Azure, then again, retrieving that from my client to go into the Key Vault store to get the secret. We need to think about these kind of things. Again, we need to think about these things when it comes to like sensitive credentials, utilizing your configs at the application level. But again, secrets should be stored in something like Key Vault. Reliability, observability, and operations. So I'll kind of cover these quickly. Retries with back off, circuit breakers, and bulk heads. This is done with Istio itself. We need health checks on all services. So in your ingress file or your YAML file to do with your Kubernetes, startup probe, readiness probe, liveness probe, health checks, all of this information, we need to make sure it's A, reliable, but if it's not, then we need to improve upon it by logging it to some sort of observability and analytics as well. So you can see here observability, but finally, we want everything to not be tied in together. So we need some sort of transactional outbox pattern, like Kafka, like the PubSub by GCP or Amazon SQS. It all should be handled asynchronously. It goes to the back of the queue and then it kind of does what it needs to do. So transactional outbox pattern ensures events are not lost. Again, if there's an outage, it pops it to the back of the message queue and then it does what it needs to do. So observability, you've got logs in here, but it doesn't really matter what logs you choose. These are the logs we have in here: metrics, tracing, alerts. It can be utilized through whatever service you have. You generally have your dashboard kind of key requests, your health checks, your whatever it is. And there's one I like is Dynatrace, but again, you can choose whatever it is for the relevant project. Most of the time, if you're working on a project, of observability is already in play, but you need to think about these. And then finally, you can see your operations here. Again, CI/CD, how you kind of automate the code, create the relevant pipelines, then deploy, create your Docker images, verify unit tests are working as expected, making sure that your end-to-end scripts are working with Playwright or whatever it is that you need, your Sonar scans, your Docker images get published and then deployed onto your Kubernetes pods in your namespace, and making sure that again the base is covered so you can have infrastructure as code with Terraform, and that just creates the services that you need. Again, with Kubernetes, you'd probably want to do that like instances or your kind of VMs that you have, and then making sure that your Docker containers are working as expected. They all have the same kind of versioning on them. All of this stuff you need to consider, and then how your kind of backups are, your disaster recovery, how you deploy as well. So how you deploy as well, you could have your canary deployments or your blue green deployments, but again, backups are important. Thinking about what I've mentioned in this video so far is replicas, availability, consistency, the trade-offs involved. Everything needs to be from a customer standpoint as well, because if something goes wrong, it's the business that fails. So again, you need to think about these things as a high level principal engineer, is understand the trade-offs involved, the SLOs, which I think I've mentioned, which is basically the availabilities of what we've discovered over here. So all of this stuff is hashing it out and then almost creating like an end-to-end design, which is what we will cover next. Right, so now we've got to the stage, we've looked at the functional requirements, we've done the non-functional requirements, we've looked at how the APIs and the user functionality will work, and now it comes to the stage of creating all of the requirements and putting them onto the actual diagram. So these are all the requirements we have here. All we need to do is just make it so that is well explained on the functional diagram, and that you understand what is going on and how everything is connected. So what I want to do is I want to kind of start from the top. So if we start with how a high level search system design works, this looks all neat and tidy, but what essentially was kind of starting point before I got to this Miro board was something like this. So if I zoom in here, basically we have a user or a client, goes to domain name server, then the CDN to serve as any static assets like your JavaScript, images, CSS, fonts, all of that kind of stuff. And then we go into our web application firewall. This is what prevents your cross-site scripting attacks and so on. And then we get into the API gateway or the load balancer, whatever it is that you're using. This is a rough sketch of what I've done, but again, this doesn't make sense right now. So again, we needed to make it a more relevant in a design. So customer goes to the DNS, then it goes to the global load balance, which again, the domain name server, it finds the service that you need. The load balancer sends the traffic to the healthy instances that you have. In our case, it'll be the Kubernetes pods. And then again, web application firewall blocks the bad traffic. It does like your whatever it is that you need to do with your cross-site scripting, DDoS attacks, preventing them. Then your content delivery network is the one nearest to you in the nearest region you're at. It caches the safe content closer to the users. Your search API validates the request and queries the search. So that's essentially what we did, refining all of the searches in the actual King's Cross itself. And then we have a distributed cache, which gives you the fast repeatable result. In that King's Cross scenario, we had our recommended ones, which were cached, and that was served. And then the API responded with the remaining ones, actually. So these were the recommended. And then the API responded with these over here. So that's cool. And then we have our search engine, which is text search filters, sorting, ranking, everything to do with the Elasticsearch cluster is over here, and then you get your results. So this is search, but again, we wanted to build the entire Expedia sort of look and feel, and also on the beach, any other travel sites, that kind of look and feel. Then part two is, and again, we're looking at the search only, but this is just a service that is being offered in our high level solution design at the end. So second part is how the search index gets updated. So it looks in the catalog, pricing, and availability systems. It goes to the source of truth, which is the database, which gives you the accurate booking product data, which then connects to like hotels or whatever it is. Then once you make the booking, you have some sort of transactional or change events that says, right, this publisher has updated, all the subscribers, do your thing, do your jobs, send your emails to the customer, update the payment providers and so on. And then that's asynchronous, so there's no lag. Looking back at the non-functional requirements, I've got here a booking confirmation less than 5 seconds, and then the booking availability needs to be that. So it shouldn't wait for anything that can be done asynchronously with Kafka or our message broker or whatever it is. The indexer transforms the data into searchable documents. So it might look for your non-relational database in your Elasticsearch, finds the relevant information. It'll probably do something like a flat map, and then make sure everything is findable with like a map to make that indexable and then probably cacheable as well. Then your search engine, your Elasticsearch, it read optimized the search model. So Elasticsearch is good for high reads, isn't it? So that's why most companies use it. And again, bookings use authoritative systems, search uses an indexed copy. So you probably will be able to see the indexes when you actually do the actual indexing. So if I was to do a quick search, it might be a response that gets returned for the indexing that happens. Or let's try on the beach actually. The beach, if I went in here, and then you can see the inverted indexing happening in the actual browser itself in the network tab. So I've actually got it on recommended. So let me just go into here and clear everything out first of all and press search. So now all these v2 type JSONs are happening. So as you can see here, this is an index that gets returned. So that's what that means. But yeah, that's essentially that. So part two is done. Part three is consistency, availability, and partition tolerance theorem. So essentially, cache prioritizes availability and speed. Data may be slightly stale. Again, that's fine for certain scenarios. Search engine, API, eventual consistency, great for searching and filtering. So we can search for stuff, but we re-verify it at the booking stage anyway. So you don't really need to worry about the availability or the consistency in real time. Source of truth database, again, consistency matters for booking and payments. We mentioned that. And then the API layer is stateless, which means we can scale horizontally behind the load balancer. So when there's high traffic, we can horizontally pod auto scale the Kubernetes pods in there, and then your message broker for any sort of external services using Kafka, we can decouple that, reduce the load times and the booking services to an SLO less than 5 seconds. The fourth one is the API design. What are we actually having as our APIs? That mostly get and post any sort of updates in there as well. The queries for the search, we've also covered the actual ones over here. So search, view holiday, booking, these are just get and post methods that you can define, query params on the relevant search queries and so on. But here's your response example. But APIs need to be clear, predictable, and filter friendly. But you also need to version them as well in case you wanted to update any of the APIs as well, so that you have your V1, your V2, and follow your best practices. API should be rate limited and all of the best procedures in place. And then five is the indexing and how the search works. So as I mentioned already, Elasticsearch has inverted index for text search, keyword fields for exact filters, numeric data, fields for price, and travel dates. Geofields for locations. So that means your geospatial indexing for your lat and long. You want to kind of hash them values and then have some sort of geofields in like a map somewhere, or Elasticsearch covers that for you as well. And then your shards for scale, replicas for resilience as well. So that's the indexing part. And then the B is your search process. So you want to tokenize the query and cache it if you can do, match hotels and destinations, apply your relevant filter and sorting logic, score and rank your results. So the best ones at the top, and then the lower ones at the bottom, and then return your results and your facets as well. So that's pretty much everything in a nutshell. And if you don't know what facets is, it's here as well. Facets are like your hotel information, so your destination, your hotel class, all of the information that you kind of need. So that's everything in terms of search on the high level system design. And again, it's just a case of creating some boxes, making sure that everything connects to each other, and then the services work as expected. You need to make sure that they're all decoupled as well. And again, each system or each service should have its own sort of logging and monitoring in place. Again, you can utilize the cloud provider of your choice for the relevant ones. And then you need to look at your annual bill or your monthly billing as well, and then have some cost optimization on each of the services as well, and constantly monitor and improve. What we'll look at next is the final architecture. So that's how service works. I'm going to go through the final architecture, and then that should give you enough of a stead into creating your own end-to-end system design. We'll start that next. Right, so now we're at the final stage, which is the holiday search and booking platform, creating the final architecture with these things in mind, which is scalable, high availability, secure, event driven, eventually consistent search, and strong, consistent booking. So let's go through it and everything we've kind of discussed going up to this period. Now we just kind of need to collate it together. So we started off with the functional and non-functional requirements and ideation and sort of the core is required along with the API design. Just a case of end-to-end final architecture, and then final deep dives as well. Starting from the user, you have your user app that can be web-based with React or mobile-based with whatever it is, Expo or React Native or whatever. You have that here. The user then connects to the relevant section over here, which is your domain name server. It points to wherever the app is, so the IP address you need. It does all of the relevant DNS, adding the HTTPS to if he has a SSL certificate and so on. Then we have CloudFront, which serves our static kind of images. If there's like a server side rendered app or whatever it may be, it kind of loads that up for you. So thinking about Expedia, it kind of has your, if you just go into actually on the beach itself, it has all of this information here. So if I go into the homepage, it kind of loads in the banners, all this kind of static information that is already there at the CDN level, and then sort of some API calls, any options in here. It kind of the entry point to the kind of app itself, and then any sort of performance based items that it needs, such as lazy loading or whatever it may be, that's done on the CDN side as well. That is that, and then if you need anything else, you can just make your relevant API calls. The web application firewall is like your security guard that kind of blocks any sort of bad traffic from entering into our Kubernetes cluster. And then once that's done, kind of loads our load balancer, or in our case, the API gateway through a service mesh, which is the Istio ingress. And basically, Istio ingress is essentially a load balancer that runs on like a proxy that acts as a kind of entry point for your service mesh here. So it kind of does what it says here. So traffic management, MTLS, observability, retries, any circuit breakers. That's essentially what it is. And then I mentioned static assets. So you've got everything in your object storage that can be sent to your CDN, and then that CDN returns it to the browser. So you don't really want to make calls to your object storage directly. CDN should sit close to the region that the user is based in, and then serve that information close to the actual customer and the region that their IP address is at. So that's pretty much that. Most of the server side rendered apps are quite good for this. So CDN, we need that part as part of the standard end to end architecture diagrams. We do need that. So that's essentially what it is. Now we're getting onto the Kubernetes cluster. Once we've done the service mesh in Istio, we want to then, or the API gateway, we want to then connect to, let's say it's a microservice architecture, we want to connect to the relevant services for that particular user. So I'll go through each service one by one. I've mentioned a lot about the search service in here. So that essentially does call it the Elasticsearch cluster over here. So parse search criteria, build the query, cache lookup, and then it calls Elasticsearch. Essentially, the search service now has its three Kubernetes pods within the relevant Kubernetes cluster, within the relevant namespace if you have namespaces in your organization. So once you've got the pods, you can first of all connect to the Redis cluster, which means if someone's done the same query somewhere else and it's kind of cached that search result, then we can serve that information, which is like something similar to the destination they've looked at or any popular data that they have, that can be cached in the Redis cluster, and then therefore it's to the customer with a short TTL, which means that it refreshes every so often based on the TTL that you set. So that you can serve that to the customer, which is quite fast. Or alternatively, if there isn't one, or the TTL is like 60 seconds and it's reached the 60-second mark, then you can go into your Elasticsearch cluster, which is your search index over here. This is then sharded, which is kind of like it's divided into five, for example, or whatever it is. It's kind of sharded so that you make the relevant calls to the relevant shard and you're not trolling through the NoSQL database to get the information that you need. And again, this is denormalized documents. So that is essentially everything from the search service. Is check the cluster first. If not, go to the Elasticsearch cluster. Thinking about cap theorem again, it just needs to be available, doesn't it? So high availability over consistency, because you're getting documents from either your Redis cache or your Elasticsearch cluster. The next service we have is the holiday service. So again, holiday details, itineraries, image and content, facility and reviews. This is pretty much static almost. It doesn't frequently get updated quite a lot. Maybe the reviews get updated quite a lot, but again, do we need search functionality from Elasticsearch? Probably not. So therefore, we have a PostgreSQL database with a primary cluster that serves all of your information. Again, this is sharded, but You can shard it in sections or however you want. And then if you're retrieving the information, it's got B tree indexing on there as well, so you can kind of segment your shards into the relevant sections like holiday information, hotel information, itinerary information, some snapshots from the prices and availability that you got from the availability service, which again you can see the arrows pointing just there, and then your reviews and so on. So all this information is there. And again, all of this connects to your transactional outbox, but we won't look at that just yet. Then you've got your availability pricing service, which is real time availability. So we do need our pods to connect to the primary cluster and then get the updated information. Again, linking to the transactional outbox. I won't worry about that too much. Again, this database now is also connected to the booking service. You can see the arrow here. What that does is essentially manages the booking. So you have a booking state and so on. So these are the three services that connect to your PostgreSQL database. So it makes sense to have that because that information is just available within relational database based on the holiday that or the hotel or the itinerary that the customer chooses. NoSQL documents, it makes sense to use the Elasticsearch cluster. So that's that part. And all the pods, they just swap in and out based on the health checks within Kubernetes. Kubernetes just handles it all, which is why I would suggest container orchestration as opposed to deploying on something like Cloud Run for stateless APIs or stateless apps. Again, because we want that high availability and reliability, the PostgreSQL primary cluster also has your read replicas in there. So you can see your read replicas now. They basically update the scaling or read the scaling and report any analytics. So it's like a backup to your SQL database. Again, going back to the booking service over here, we've got something called the item potency store, which essentially is this booking state machine, which we looked at earlier on, that says Redis slash PostgreSQL. So it looks into them. It adds the item potency key, which means the booking ID status response, to say this customer's making this booking, make sure they don't get charged twice. And that's done with the item potency key. So we have to think about that as a requirement for the customer. You're creating a manual process there where you need to look at the payments the customer's made, however many times. A, that's bad for your reputation as a company, and B, you got manual work to rectify it and correct it. If you made the booking twice or whatever, or will the availability of the books or the rooms change for other customers? Probably. You need to consider these things, and then obviously the manual processes of refunding the customer and so on. So it's very important to have that one in there. And then again, when you're doing your booking service, having some sort of timed kind of frame, which I don't think I've added on this diagram, where it gives you like 60 minutes to make that booking, to say, right now you're making this booking, there's 3 rooms available as opposed to 4. Plane has 4 less seats available because there's 4 people going on the holiday. You get the picture with that kind of hiding that information as a lock, and then kind of once it's confirmed, once it meets here, once the payments happened, then it's updating all of that within your transactional outbox event bus over here, but we'll get onto that in a moment. And then finally, let me just zoom out a little bit and then scroll across. Finally, you've got your user account service, which again is just a service to handle the user profile, authentication, any sort of preferences, logging into their service as well. So that's essentially it. This line here I've missed, which is the payment provider step, which is part of the booking state machine, so that if it's confirmed, item potency key is there, everything gets updated based on the booking service. All these services link to your PostgreSQL database. Then it goes to your transactional outbox over here. So this transactional outbox triggers or kicks off or sends messages for anything that has been updated. For example, here you can see the aggregate type, event type, payload status created. The holiday was updated. The booking was marked as pending. This creates your log basically of what has actually happened in your CRUD methods within your services. So let's just zoom out of that. And then I want to go back onto my event bus, which is utilizing both. If I was to go over to the availability pricing services, and then I've got this line here, which kind of connects all the way to the supply integration layer, which is our APIs. So all the services connect our APIs, and then it basically updates everything, and then it kicks off an event bus, which basically means if anything happens, just such as a booking, it kicks off your event bus. or PubSub or SQS or EventBridge or whatever it is, kicks off your updates to your relevant services. There's more services than that. Right now, I've got cache updater service in here that then links all the way up to the Redis cluster. The Redis cache can be available on multiple services. So it could be on the holiday service, it could be on the pricing service. So what I should have added in this diagram is this Redis cluster, each service should have one as well. Availability and pricing service, that needs to be checked all the time. So that needs to be real time. But again, you think about the complexity involved in all of this kind of information in here, where you need to think about all of these things. And then event bus sends the cache update, updates the Redis caches, that's fine. It also sends notifications such as your booking states, which is what we mentioned in here. So, like, it could say payment authorized as an email to the customer, or something like your holiday is being booked. Then that holiday will have some sort of countdown timer in there to say this is the up once we booked. So it's not in the requirements in here. So that's out of scope. So think about all of these end-to-end kind of scenarios that go on. And then event bus again, pub subtopic. It could send emails, it could send text messages, it could send promos, whatever it is. If there's an update in any of the services, then then event bus says, right, it's looking at the APIs over here and it's saying, okay, users updated their preferences to change the telephone number. Event bus sends that text message to kick everything off. So that's essentially what it is. So that is everything within the Kubernetes cluster. What I'm going to look at finally is any cross-cutting concerns, and then we'll talk about the final sections of the overall design, which we have covered in our requirements, and we'll look at them next. Right, so now that's the overall end-to-end architecture done. We also need to consider any concerns that we have or edge cases or any deep dives as well. So these are the ones I've kind of got here, which were covered in our functional requirements, but I'll go through them again. So we need to think about security from a secure standpoint. TLS everywhere, everything is encrypted, making sure we have OAuth 2, identity confirmation, JWT validation, especially on like the user side of things when we're logging in. We also have RBAC, which is role-based access control, so you can only access what you need. Secrets Manager, which is getting the secrets from somewhere like Key Vault. So that's Secret Manager. Then I'll let you research the rest, but essentially we just need security everywhere, and that kind of is handled based on your cloud provider. You can set up like your infrastructure as code to make sure that this is all secure. Again, utilizing AI to help with this kind of stuff helps as well, and making sure that everything is robust and secure in every way possible. Then we've got observability. I've talked about this as well, where we kind of need logs, metrics, tracing, dashboards, and alerts on every step, whether it's any sort of status code, success, errors, anything like that. From start to finish of the user's life cycle, we need to be able to monitor and alert so that we can improve our code. It's more robust, identify gaps within the logs so that we can either save costs, improve efficiency, and make sure that everything is alerted. And if there's anything that fails, then again, alerting is important because we have the relevant people that get notified, or the relevant service that gets notified. Then we can kind of manage the situation based on the severity of the issue at hand. I think again, dashboard, tracing, all of this information for observability. We basically need to keep an eye on everything in the actual overall architecture to make sure it works as we intend and expect. And also, we want to be sustainable, think about costs, reducing costs, and overall the customer experience as well. So that's observability. Then we've got reliability, which is again, Istio handles the retries, backoffs, circuit breakers, timeouts, bulkheads, but we also have the health checks, which again relates to our observability over here. And then reliability in terms of our pod healthy, or is our versioning updated, anything like that, we need to be reliable with the services. Again, going back to the cap theorem, which I'll go to at the bottom over here, we'll go to that in a moment. But then finally, our operations. So do we have backups? Do we have disaster recovery, horizontal pod auto scaling, vertical pod auto scaling? Do we have infrastructure as a code, no manual processes, so that everything is reusable, predictable in terms of our starting points? CI/CD from GitHub Actions, or it might be whatever it is the on the cloud service that you use. It could be GitHub Actions, it could be GitLab, it could be whatever it is. Operations, they need to be, again, scalable, robust. They all should have a reason for being there. These are kind of, I'd say everyone needs, along with the infrastructure as code. Nowadays, you can utilize Claude AI or whatever the GPT model it is you're using, Claude Code, to generate or create the relevant infrastructure as code that you need. Again, we need manual reviewing for most of the AI stuff that we have. We shouldn't just let it hallucinate. We need to verify this. We need the relevant guardrails and standards in place, and also making sure operations are scalable as well. So that's essentially the edge cases or the concerns that we could have. And then finally, API design wise, everything should be versioned. So have a version on there, add your rate limiting on there, add your API kind of standards that you need. Along with that, consistency using CAP theorem. So search is Elasticsearch, high availability, eventual consistency, which is fine as a trade off that we have. Accept small staleness, which is a few seconds that you can return stale data with a TTL in there. And then for booking, you can use your SQL database, which is Postgres. And then that strong consistency and correctness over availability, because we want to make sure that the user gets charged the right price, updates the booking information, the flights on the plane, all of that kind of stuff needs to be considered when it comes to cap theory. For scaling and SLOs, actually, stateless services scale horizontally, again, with your horizontal pod Kubernetes auto scaling. You have read replicas, which is essentially clones of your PostgreSQL or backups. Elasticsearch shard and replicas. So the shards are the inverted indexes that can go into the shards to get the fast results, which is the low latency, and then the replicas is just the backups of your shards. Your cluster for high throughput, because you need cached information or data wherever it is when necessary, with a short eviction policy of like a TTL of 30 seconds or whatever it is based on your SLO over here. Your CDN for your static assets caching, again, that's just a no-brainer nowadays anyway for serving static content, along with your SLOs, which we've discussed already, such as your availability times, your latency times, your availability for your bookings, and so on. And then finally, your key data flow. So if it's a synchronous request response, we want to handle that. Asynchronous events, handle that through Kafka or anything that you utilize, such as PubSub. And then again, we need to manage the external and third party flows as well. So I'm just going to zoom out, and that is the high level holiday search and booking platform design. So the reason I've done this is because when you get to this principal level, what you want to think about is the overall architecture and delivery. And most of the time, let's say if a kind of user is here, and in my channel we focused on a lot of this user type stuff, so building your front end, back end, and so on. I've delved into a lot of GCP as well and Azure, but what I want to do now is scale out and help people understand or help you improve on creating these architectural diagrams. This is what separates you from others. Understanding things like Kubernetes in here, understanding Istio Ingress, API gateways, any edge cases, functional requirements. All of these things help you improve your understanding of the overall kind of end to end architecture and patterns. So, again, hopefully, this has helped you understand how just a small thing like a search platform like On the Beach or Expedia or Booking.com, whatever it may be, from off with your notes, which are in my VS Code here, you get to your kind of functional and non functional requirements. You have your draw your diagram, which is what I created, is this diagram over here, which isn't the best and it doesn't explain anything, but then you kind of connect it and compare it in a Miro board like this. Obviously utilize some AI for your like icons that I've had in here and make sure it makes sense, understand how it all works, and then it's about understanding end to end how you explain it to whoever it is you're explaining it to, so that even you understand it and the trade-offs, the kind of pros and cons on why you chose a selected item. This is the high level thinking that you need to understand and how it works. And there's a lot on this diagram that I have missed, and I'm aware of that when I was presenting it. But again, this is just the basics of what you kind of need to cover and make sure. But each of the services here is its own thing in itself. So a search service is massive, holiday service is massive, This is where feature teams get involved. You have your feature teams in your company that build all of these services. It's that person that kind of does the high level architecture that connects it. So that could be a solution architect, whatever it may be, your principal. You need to understand this type of stuff if you want to get into the big leagues. I want to kind of help people understand this and keep it simple and high level, but also delve in deeper to any sort of concepts. Be missing that is its own topic itself. So Kubernetes is its own thing. Then you go into databases. Databases have sharding, inverted index, geospatial index, B trees, all of that kind of information I want to go into. Payment providers, again, that has a lot of information in there. Clusters such as Redis for caching, that has a lot of information that you need to learn. It's quite a lot and it's quite daunting at first, but what I want to do is I want to bring this to life and make sure that everyone understands it. And then from a business point of view, you have SLOs in there that you define as these are the standards that we have in place. Blue green deployments, your CI/CD. I've covered most of the stuff to do with on my channel, but I want to kind of create simple, easy, understandable topic. Even things like event-driven architecture with a Kafka or whatever it may be. I want to go into much more detail, but hopefully this is a starter to help you understand that this is how high-level principal engineers think. They might even think even deeper than this, but the point I'm trying to make is this is the kind of level you need to be aware of end to end. You've got your full stack, you've got your cloud, you've got your SRE type capability, you've got your solution architects. It's kind of covering it all, but again, we'll get there in smaller chunks. And what it's all about is creating these small chunks to learn from. So hopefully this video is helpful. If you liked it, give it a like. And what I'm going to do is I'm going to create more of these kind of final architecture type items on my Medium blog and also on my LinkedIn. So if you don't follow me on there, give me a follow. We can connect and come and say hi to me. And hopefully, let's just learn together and improve together. And then I'll try and put more videos out like this. And please like and subscribe. I'm going to try and be more consistent on this channel. So, yeah, give it a share, follow it on all channels as well. And then all I'm going to say is take a look at this. I'll include all of the links in the video. Please like, share, and subscribe. And then I'll see you in the next video.